Good morning. In the last class, we have discussed about the step-by-step procedure of Nyquist plot criteria. So today we will talk about the step 3, that is analytic function and singularities. So what is meant by analytic function? So when a function is said to be analytic, suppose a function say f of s is said to be analytic, is said to be when it is going to be said to be analytic. Okay, so a function is said to be analytic if in a plane, if its value and its derivative have the finite existence at that particular point. So if you take this example as f of s is equal to, that is 25 by s into s plus 1, means, see here, for s is equal to 0, for s is equal to 0 and s is equal to minus 1, these, for these values, this function will give the infinite. This function is gives the infinite. So this function is said to be analytic at all the points, except these 2 points. Why? Because except x is equal to 0 and s is equal to minus 1, this function will give the infinite values. So if I want to set a function is said to be analytic, it has to give the value. I mean, it is a finite value. It should give the finite value at that particular point. So there should be a finite value at that particular point. So if we give the x equal to 0 and s equal to minus 1, then f of s will become infinite. So it will not be analytic at these 2 points, and remaining all the points, see, at all the points it will be analytic except this x is equal to 0 and s is equal to minus 1. And also a function f of s, we have talked about the analytic function now. So analytic, what is meant by analytic function? Now what is singularity? Means single value function. A function which has the single value. A function which has the single value. So when it is said to be single valued, say for example, if I take f of s is equal to, say, square root of s, and for s is equal to if I give 16, for s is equal to 16, so f of s will become square root of 16, and which has the plus or minus 4. So it will be having the 2 values, that is plus 4 and as well as minus 4. Though this will not be, this function will not be called as single valued. This will not be called as single valued. So in this in this control system analysis, what we do is, what we assume that the transfer function of the system are the functions of g of s and as well as h of s are single valued. So we assume that this single valued function, this g of s and h of s, we can call it as single valued function. We assume this is the in a control system analysis. So now we have understood what is meant by analytic, and what is meant by analytic function, and as well as what is meant by single valued function. So analytic is nothing but is the function which has a finite value at any point. So then it is said to be a analytic function. But if you take this example here, if you look at this s is equal to 0 and s equal to minus 1, this function will become infinite. So at those points it will not become analytic, and other than these 2 points it will become analytic. So at all the points except s equal to 0 and s equal to minus 1, this function f of s is said to be analytic. F of s is said to be analytic. Similarly, single valued function means, so it should not contain for the same s value, it should not contain 2 values. That is, f of s should not contain 2 values. So that is what we can call as it's not a single valued function. So but in a control system analysis, the g of s and h of s which you are giving will be called as single valued function. We assume that g of s and h of s as single valued functions. Now coming to the next step, that is principle of argument, or Cauchy's principle of argument, or mapping theorem. We can say it has a different name, mapping theorem or principle of argument, So if you take this mapping theorem or principle of, who has developed this principle of argument is by Cauchy's. So it is also naming as, so what it states. So the mapping theorem states that suppose f of s is a, I have taken as f of s is a single valued and analytic function at all the points, except at all points except we can take that some points, right? At all points except that some of the points where it is going to give the infinite value, where it is going to give the infinite values. So మీరు చెప్పండి, నేను ఆన్ చేస్తాను. రికార్డింగ్ ఆఫ్ చేయాలని రెండు వీడియోస్ అయిపోతాయి అప్పుడు. జస్ట్ టైప్.
Hello.
No, I just you just put it in chat box. Details you put it in chat box. అది 7 గ్రూప్ వేసే వేసినావు కదా, ఏం అవసరం
చెప్పేసి
అక్కడ ఉండేది చూడు ఎంతమంది వేస్ట్ వద్దు. ఓకేనా?
ఒకసారి చెప్తే
Yeah. So f of s is single valued analytic function at all the points in S plane. What we have taken is except some finite number of points. That's what we have taken example, that is s equal to -0 and s equal to -, where it has a f of s has the denominator roots that will except those denominator roots. This is assumed as a single valued analytical function. Now these are singularities. We can say these are the singularities of function f of s, which where it is not analytic, because if you have the singularities in the f of s, means which gives the single valued function where it is not going to be analytical. So now consider a path, a tau of s, which is we are going to take say for example an arbitrary path. We are going to choose the arbitrary path. This is tau of s. So what we are doing, we are considering an arbitrary closed path in S plane. So this is the S plane. So in the S plane, we have the real and imaginary axis. Okay. So in such a way that this f of s is going to be analytic. So when I want to say f of s is analytic, this f of s which will be having the denominator roots. So this path should not pass through this denominator roots. So then only we can say f of s is analytic at each and every point in the tau of s path. So at each and every point. So it means wherever the points are there here, all these points, at these points it will give the finite values. Suppose if you take a point here, so this point will not be passing through this tau of s path. So this will not be said to be analytic at this particular point, because if it is analytic at this particular point, then this has to give the finite value. So if I take the poles of this function, which is passing through this f of s function, f of s denominator roots are called as poles of the function, poles of the f of s function. So if I passing through the poles of this, then the f of s will become infinite. It gives the infinite values. So this f of s is analytic at each and every point on the tau of s we have taken. And but the restriction is to select a path. How to select this closed path restriction? What is the restriction we are going to take? What is the restriction we are going to take on this? How to choose the closed path? How to choose the closed path? Right. So in this tau of s, which are say generally it will be taken that should not pass through the points. It should not pass through the points. The tau of s should not pass through the some of the points which are we can take it as singularities, which are singularities of f of s or f of s. That is, it should not pass through the poles of f of s. If I take the f of s, which is p of s by q of s equal to 0. So means this is called as poles. When the q of s equal to 0, then we can call it as poles of f of s. That's what he's saying. So here, this should not pass through the points which are singularities of f of s, which you can take it as q of s. So So for the q of s, means that will be taken as poles of f of s, which should not pass through the poles of, say for example, these are the poles which is having. So it should not, this tau of s which you have chosen, that should not pass through these poles of the f of s function. Such a way you need to draw arbitrary path. This is called arbitrary. Randomly we have taken the path which you have to choose is a closed path. It should be a closed path. It should be a closed path, and from where you start, and then but it should not pass through the any of the poles of f of s. Okay. So now let me take how explain by taking the poles and zeros of this system. So for example, yeah. So take p is, let p is the number of poles. P is the number of poles encircled, means which are inside the path, encircled by tau of s, and say z is also number of zeros which are encircled by tau of s, Now, according to the mapping procedure, what we have discussed till now, the closed path in a S-plane can be mapped into other plane, that is we can call it as F-plane. So how to do this? How to do this mapping from S-plane to F-plane? Say how we are going to do this S-plane to F-plane. We are going to find out this mapping, means that another path which is in the F-plane. So that we take one example and then we do. So here if you take the P and Z, which are encircled by this P and Z is nothing but number of poles and number of zeros which are encircled by the tau of S path. But here we are interested in how this f of f plane it is going to be drawn from the S plane to F plane. How we are going to map it? So with this one, we are going to explain with the example here. Yeah. So I'll be taking f of s is equal to say 10 by s into s plus 2. So this is one f of s function I have taken. So where we can plot the S plane. So this is the S plane. So where real axis and then imaginary axis. So here if you locate all these poles, which is at s is equal to 0, at s is equal to 0, one pole is there, and at s is equal to -2, say it is one more pole. Okay. So here these two, if I choose the arbitrary path, which is it is taken as tau of s path, which is arbitrary path which is chosen. Other than, see, it is this tau of s is not passing through the point s equal to 0 and point s equal to -2. So we can take it as this is a arbitrary path. So now we have selected a closed path in this S plane such a way that it is encircled. So these two, as we told that in the beginning, so these poles has to be encircled by this arbitrary path which is chosen tau of s. So we have encircled at s equal to 0 and as well as s equal to -2. Now the function f of s, this will become is analytic except what? Except at s is equal to 0 and s is equal to -2. So it has and it will be taken because these 2 points it is not passing through this. So now this tau of s, that is this path is not passing through these poles. So we can say f of s is analytic at all the points, and here if you take the p is equal to how many poles we have, p is equal to number of poles is 2 and z is equal to 0. So there is no zeros. Now for each point on this tau of s, for each point, if you take the points on this tau of s path, it has the value, the f of s will be having the value. So for example, if I take at s is equal to say for example, this is, I'll be taking this point as s is equal to j2, say s is equal to j2. So what is the value at s is equal to plus j2, means plus j2 and as well as, and I'll take this point as, say for example 1, and then this is going to be 2 at s is equal to 2. So at s is equal to 2, and at, I mean plus 2 here, because this is the real axis, and here it is imaginary value, that is s equal to z2. So at these 2 points, if I find out the f of s value at s is equal to 2, that is 10 by 2 into 4. So I'll be getting 5 by 4, which is 1.25. Means in the f of s plane, if I take this f plane, see here, this is the f plane, because we are taking the values of f of s. So by substituting the s value, by substituting the f value, so it is going to be 1.25. It is going to be 1.25. Similarly, at s equal to z2, if I find out, so f of s is equal to 10 by s replaced with j2, and then j2 plus 2, so we can find out this value by rationalizing, that is divided by minus j2 into 2 minus j2, 2 minus j2. So here minus j2 into 2 minus j2. So if you rationalize this function, so then I'll be getting the value where it exactly the f of s at j equal to, I mean at s equal to j2. So here 10 into minus 4 minus j4, then minus into minus plus into j square 4, so j square 4, then divided by plus j2 into minus j2 is minus j square 4, and this one is going to be j2, a plus b into a minus b, so j square 4 square, so a square 4 minus j square 4, j square 4. So if I substitute here 10 into this, j square is equal to minus 1, so minus 4 minus j4 divided by, here j square is minus 1, so plus 4 into this is going to be minus 1 plus 4 plus 4 is 8. So here I'm going to get so 4 in 2 2s are, then 5 2s are, so 5 by 16. So 5 by 16, so minus 20 by 16, then minus j20 by 16. So it means that I'll be getting around 4 4 ja, 5 5 ja, once again minus 1.25 minus j 1.25. So in the f plane, for the value of s equal to j2, for a value of, see, this is the s plane, this is the s plane which you have drawn. So here s equal to z2, for the same value we are going to get, for the same value, that is s equal to z2 in the f plane. In the f plane I'm getting minus 1.25 minus j 1.25. So minus 1.25 minus j 1.25, here I'm going to get, so this is say minus 1.25, and say this is minus 1.25 j, minus 1.5 j. So here this is the point where I'm going to get. So if you look at, the path is going to be for the value of, when I'm trying to take the values in what direction, so the direction which I'm taking is in this direction, means the first point is here, then the second point is here. It is in the anti-clockwise direction I have taken. In the anti-clockwise direction taken means the first point, and this is the second point, right? So these points which I have taken in this anti-clockwise direction, so here the value is moving in this direction, mean clockwise direction. So s plane and f plane, it is going to be mirror image. It is going to be a mirror image. So in this, if I join to these points, and then if you plot all these points, it is going to be giving in a clockwise direction. So it is giving as a clockwise direction. For all the values, if I calculate like this, then it is giving in this direction. So similar to this, if I draw the f of s plane, for the different values of s in the s plane, if I plot the f plane, see here, I'll show the difference. So if this is the s equal to 0, and say this is going to be a minus 2, wherever you take, this is the point if you have taken in this direction, that is in a clockwise direction. For every point on this, this is s plane. For every point on this s plane, if I calculate the f values, that is, this is the real axis and then imaginary axis. So here f plane, in the f plane, I'll be getting exactly opposite direction. That is same with the different values. The different values of yes. So here it is going to be clockwise. Here it is going to be anti-clockwise. So for the value of different s values on this path which you choose, and if you calculate the f values in the f plane, then it is going to give this is in anti-clockwise direction. This will become clockwise direction. So exactly it will give the mirror. It is going to give the mirror value. So this procedure which you can call it as a mapping. It is called as a mapping procedure. This is called as mapping procedure of a one point in the one plane to the other plane. That is what you can call as f of s. And this f of s is which you have taken as called as mapping function. It is called as mapping function because we are taking from s for different values of s with another f plane, So we get a closed path which is I'll give naming as say tau dash of s. This is what we can take it as tau of s, and this will be taken as tau dash of s. So here tau dash of s, which is mapped locus, it is the mapped locus of tau of s. It is the mapped locus of tau of s. That is what we can say which is mapped to the this tau of s function to the tau dash of s in f plane with the help of this mapping function f of s, with the help of this mapping function of f of s. So here the mapping theorem which is actually related to this mapped locus of tau of s plane, So now you can say what it says. The mapping theorem states that this mapping theorem which you have discussed, that is mapping procedure we discussed, but mapping theorem states that the mapped locus, that is mapped locus tau of s encircles, this is the new origin, so encircles the new origin of f plane, as many times as the difference, as many times as the difference between number of poles and number of zeros, that is number of zeros and number of poles, that is how many times this tau dash of s is encircled with this origin. So how many times it is encircled means, suppose if I want to find the number of encirclements, this tau dash of s, not tau of s, it is a tau dash of s, how many times it is encircled by the origin will be calculated by using n is equal to z minus p. So this is very important, where the number of this n says that number of encirclements of origin of f by f plane by the tau of s path, tau dash of s path, not tau of s path, tau dash of s, because this is the tau dash of s path and this is the tau of s path which is in the s plane, and which is in the f plane we can take it as tau. So here this tau dash of s path, how many times it is encircle this origin, so that will be given by n is equal to z minus p. So where p is the number of poles, f of s, number of poles of f of s which is encircled by, so this z is we can take it as number of zeros of f of s which are encircled by tau of s path in s plane. See here n is calculated for tau dash of s, and p is nothing but number of poles of f of s which are encircled by tau of s path, in s plane. Means which you can take it as in the previous case, there are two poles which are enclosed by where there are no zeros. In the previous example which I have taken, that is s equal to 0 and s equal to -2, for f of s is equal to 10 by s into s plus 2 I'm telling. So in this case we have enclosed this tau of s path is 2 poles. Here z is 0, z is 0. So in that case the number of encirclement by the origin will become 2. Encircles going to be 2. So so with this we can call it as, this one is called as principle of argument. This statement is called as principle of argument, which is, that is, tau of s encircles the new origin of f of plane as many times as the difference between the number of zeros and number of poles of f of s which are encircled by tau of s path in the s plane, so that is, we have expressed in the mathematical expression, that is n is equal to z minus p. This is called as principle of argument. So here, in order to understand this, what actually this mapping theorem says, so we take an example so that we can understand how many encirclement by the tau of s path around the new origin. So here we take this example. There are, if you take this, there are 2 poles and 1 0. So in this case, there are different cases where case 1, which is, so here case 1, p is greater than z case, means that there are 2 poles and 1 0. There are 2 poles, 1 0. So here let only one pole is encircled. One pole is only encircled. In this case, I am taking no zeros are encircled, without any zero encirclements. So here p is equal to 1 and z will become 0. Actually, there are number of p's are 2 and number of z is going to be 1 here. But here encirclements we are talking about. In the encirclement, I am taking only here. If you look at only, I'm taking only 1 here. I'm going to take only 1 here. So and there is no without any zero encirclement. So what does it mean? Say if I draw a path, in the s plane, say for example like this, at s is equal to 0 and s is equal to -1 we have, and s is equal to -1. So we have this 0, and we have taken one more is -5 here. At s equal to -5 on pole, and at s is equal to 0 1 we have. So what I am telling is here, this tau of s path which is taken arbitrarily, see, it is enclosed by, see, this is enclosed only one pole. So we are taking here, let only one pole is enclosed. See here, this is the only one pole which is enclosed. So I am taking one pole is without 0. 0 is outside this tau of s path. So this is the tau of s path. I have considered this is the case 1 where p is 1 and there are no zeros are encircled. So only one pole is encircled. When only one pole is encircled. So here this relation is mentioned, that how many poles are encircled, how many zeros are encircled. So there is only one pole is encircled and 1 0. So it will p is greater than z. So that is why p is greater than z. So in this case, if I find the f plane, in this case, I'll be getting a 0. Say for example, as I told, that n is equal to z minus p. So how many z? Z is 0 and p is 1. So 0 minus 1, so it will become -1. Minus represents the clockwise direction. And number, this one says the number of encirclement about the origin. This is the origin O F plane. So if I take the new tau of s path, which is like this, so which is in a clockwise direction, like this. So it means that, so there is -1 means number of encirclement about this origin is only 1. So if you take any point on this, see, we found that number of encirclements. So here if you take this point is in this direction, so arrow if indicates, this shows in a clockwise direction. That means that it is having only one encirclement about the origin, that to be in clockwise direction, So we have taken the clockwise direction as negative. So this is the case 1. So similar to that, if you get similar to that, if a case 2, so case 2, if I take, that is p is less than z, means I am encirclement. Encirclement is this taken as 0 is taken as into the consideration of this path. So now if I plot this in S plane, so that is S plane, and S is equal to 0, and at S is equal to -1 we have, and at S equal to -5, one pole we have. So here the encirclement P is less than Z. So it means that I am taking 1, 0 is encircled, 1, 0 is encircled, and no poles are encircled, no poles, without any pole, without 1, 0 is encircled without any pole, without any pole. So if you consider this statement, so here if I draw the tau of S arbitrary path, so it start from like this, it means that this is the tau of S path, which is taken as this. So now if I draw F plane to this, so number of encirclements which I have taken as n is equal to z minus p. So whereas z is what, 1, and p is 0, so it is 1. So if you take here 1 is the +1 is talks about the anti-clockwise direction. So this is +1, so it is anti-clockwise direction. So F plane, so about the zero, I'll be having tau of S path. If I plot, there will be only one encirclement, where we can take this in the clockwise direction, sorry, anti-clockwise direction, because it is a positive. So if you take any orientation here, the direction is this one, so it means nothing but +1, So this is what we can explain with this particular encirclement, means the tau of S, tau dash of, this is the tau dash of S. So this is the tau of S as, this is F plane. So this is what we can say mapping theorem. How this mapping can be explained. This is S plane to F plane. How you map this? So based on this condition, n is equal to z minus p. So we can get to know how many arbitrary. This is arbitrary path. It is not exact path. We can say arbitrary path. About the origin, how it is going to be encircled. How is going to be encircled. Suppose if you take the case 3 case 3 where is equal to p is equal to z. Case 3 talks about p is equal to z. Okay, in this p is equal to z case, so I am taking the S plane once again. So S equal to 0, and S equal to -1, and S is equal to -5. So there is only one pole, and 0 I am considering. So in the tau of S, so for example, I have taken, this is the path which is tau of S. Okay, tau of S path, this is, see, there is one pole is encircled and 1, 0 is encircled. So 1, and this is also 1. So if I find out the n is equal to z minus p, 1 minus 1, it means 0. So there will be no encirclements. There will be no encirclement in the F plane about this origin. Means, see, if you take this path, it will be anywhere like this. So there is no encirclement about the origin. There will be no encirclement about the origin, and also we'll be not knowing how the direction is, tau dash of S. Only, and see, if you know this direction of this tau of S path, then only we can get the tau dash of S path direction. So this is the different principle of arguments, how we can explain for the different conditions. That is, p is greater than z, p is less than z, and p is equal to z case. So today we'll stop here, and we'll discuss the Nyquist stability criteria in the next class.